We use S when we go left to right in a KSP. We use X when we go right to left. And so, well, here, if you're getting stuck starting this, one of the things that we can do to simplify, this is two equilibria. So when we have this type of situation where we have a KSP and a KF, then we try to avoid doing stepwise or simultaneous. You know, if you start doing stepwise, you're asking for wasting time. And if you do simultaneous, the math is just too hard. And so when we're dealing with a KSP and a KF together, we should do a KSP. In other words, we should do the combined method. The same goes for acid. We'll talk about that later. Because pH will influence the solubility of this as well. But the other thing is that we saw we have the KF for the hydroxide. So I guess 6 molar, 6 molar sodium hydroxide will have a pH. The pH of 6 molar sodium hydroxide is actually above 14. But going to this now, what we see is the KSP is small. If the KSP is small, we're going to generate very little zinc and hydroxide, but zinc. And the KF is large, so whatever zinc's generated will be consumed. So what we can do is we can just combine these two equations to come out with the zinc hydroxide solid plus. Now, we have 2 hydroxides produced here, 4 hydroxides there, so net 2 hydroxides here. This is going to go to ZnOH4 minus the tetrahydroxyl zinc K2 ion. So the combined will be KSPF, and that's going to be this times this, the KSP times the KF. KSP times the KF is going to give us what? So we got 1.2 times 10 to the minus 17 times 4.6 times 10 to the positive 17. 5.52. 5.52 is just kind of a mix, an even mix of reactant and product here. Now, how do we start this ice table? Well, the thing here I'm doing is I'm going to add it to the solid. And so I have some solid zinc hydroxide. And then to this I'm going to add the 6.0 molar sodium hydroxide. And so what I'm going to do, and I set it up this way so I don't have to do one step. I mean, I could do it, because if there was water already present here, then I'd have to deal with the solution dilution, and I'd need to do a step I. But what we always do is we just assume that when the solid dissolves in the liquid's volume doesn't change much. And so we just assume that the liquid's volume is going to change negligibly by having additional solid dissolved in there. And so what we can do here is we can skip the solution dilution and say, okay, we're adding 6.0 molar straight to the zinc hydroxide. Now let's say let's say I had 100 milliliters of water in here. If I had 100 milliliters of water in here, I better do a solution dilution, because it's no longer going to be 6 molar. It's going to be way less than 6 molar. And that's going to have an impact on where this equilibrium lies. Now, what we say is that none of the zinc is dissolved. If none of the zinc is dissolved, then we haven't formed any zinc tetrahydroxyl zinc ion. Now comes the change. The way we visualize it, I'm going left to right. So what I'm doing is I'm dissolving the solid. When I'm dissolving the solid, what's the max I can dissolve? The max I can dissolve is called its solubility. And so this S is the max. And so it's going to be plus S. Oh, this is minus 2S, sorry. Minus 2S plus S. I meant over here. This is the max I can dissolve. And so S is, and so this is why we call it S, because we're going left to right. Left to right is how much of the solid can you dissolve. If we're going right to left, if we're looking at a precipitation, that we wouldn't use S, we'd use X for that here. And so equilibrium is going to be 6.0 minus 2s molar and s molar. Well, where do I put in the 10 drops? Where I put in the 10 drops, you know, that screws people up all the time, is people want to start with that. In chemistry, you're trained. What is the given? You start with the given and they add converting factors, or you work it, you know? The same thing with the 1 gram, you know, the 1 gram the other day I was talking about. People want to start with that. There's 1 gram, you can calculate how many moles you got, you can do all kinds of stuff, but it's not the place to start here. The place to start is just like this, you know. When we did this calculation for the solubility, you know, how many grams dissolves in 10 drops of water, did we put in 10 drops of pure water here in the ice table anywhere? No, but you know, the temptation is there because I have a fixed quantity of water, right? But we take care of that later. And the same thing here, this is just to emphasize this because we have a habit of starting. And so the same thing here, I have 10 drops of 6 molar. Well, 10 drops of 6 molar, is it okay to put it 6 molar here? Shouldn't I convert how many millimoles of hydroxide I have and use the millimoles of hydroxide in my ice table? No, if you start using millimoles, you're going to get all screwed up, basically. Here. Don't use millimoles here. People try to do it because they think 10 drops of 6 molar will give them a certain number of millimoles. 60 millimoles. But anyway, we'll just continue with this. And so it's not that we'll take care of that later. We're interested in the solubility. You know, how much dissolves? How much dissolves is a solubility question. You know, how much dissolves in 10 drops? 1 gram dissolves in how much? You know, those are all solubility questions. And so we can calculate the solubility easily here, just like we did for pure water. We calculate the solubility there without too much difficulty. And we'll do the same thing here. When we calculate the solubility here, then this is going to KSPF is going to equal the tetrahydroxyl zinc gate ion concentration divided by the hydroxide ion concentration squared. And so this is just going to be S divided by 6.0 minus 2S quantity squared. All right, so we have some math, but the math is not terrible for this particular problem because it's just a square. Now, should we shift it? Should we reset it to the right in this case? No. In fact, resetting it, like we could have reset the previous problem, but well, let me tell you, resetting can lead to complications because what do we do with the solid? You know? Sometimes we ignore the solid, we call it infinite solid. And so if we reset it, there's plenty of solid to reset it any direction we want. But in the previous problem that we did the other day, I had 1 gram of solid. So how do we reset with 1 gram of solid, not an infinite amount of solid, you know? And there it becomes a little bit more tricky. And then what is the concentration for that? And so you'll notice I didn't reset, you know. For the KF problems alone, I always reset those. And for KSP problems alone, I always reset those. But for KSPF, resetting sometimes is a little bit tricky. So for right now, I'll just avoid talking or doing it. And so here, actually the math is not difficult, so there's no need to reset this. It's going to be 6 squared is 36 minus 12 is minus 24s plus 4s squared. And so let's get this into quadratic form. And that way we could just use a solver for that. And so 36 times 5.52. 36 times 5.52 is 198.72. 198.72. And then 24 times 5.52. So it's 24 times 132.48. So this is minus 132.48s. And then 4 times 5.52 is 2208. So plus 22.08 s squared is equal to s. let's subtract an s from both sides, and make this side equal to 0. So this is going to give us 22.08 s squared minus 133.48 s plus 198.72 is equal to 0. And so we'll go to quadratic. Over here on math is fun. And then we'll plug it in. 2208 minus 133.48 plus 198.72 gives us two x values, 2.6533 and 3.39. And so x is equal to 2.6533 or 3.3. 3.391. 9. There's more digits here if you want to carry more digits. This should be plenty. And so we have to figure out which x it is. And, so we go back over here and we take a look at the restrictions. One of the restrictions here is that s cannot be greater than 3. The maximum value for s should be 3 because 2 times 3 is 6. 6 minus 6 is 0. If s is bigger than 3, we're going to get a negative molarity here. Negative molarity is what this is. And so we'll eliminate that. And then we'll have this as our s value. S, not x. Okay, so this is going to be 6.0 minus 2s. Well, 2 times 2.6533. So 2 times 2.6533 gives me 5 minus 5.3066. And so this is going to give me 0.6934. 6934 molar. And then this is just S, which is 2.6533 molar. And then we'll just double check these. So double checking these, I'll just put this divided by this squared. So 2.6533 divided by 0.6934 squared. And I get a K equals 5.518. 5.518 is supposed to be 5.52, and so that's good. Right here. All right, now what do we do? Well, the question wasn't what is the solubility. The question is how many grams of aluminum hydroxide will dissolve in 10 drops of 6 molar sodium hydroxide. And so here, now that we have the solubility, we can calculate that. In fact, once we know the solubility, we can calculate, how much dissolves or how much solvent is needed, etc. And so here, we need to do a secondary calculation, a second calculation in which we take our 10 drops of solution. Now, all the solution is going to come from the sodium hydroxide. So whatever volume the sodium hydroxide is going to be the volume of the solution. And so this is 10 drops of solution, which would be the same thing as the drops of sodium hydroxide. But in that solution, this is what we're going to have. We have to look and this is molarity, so let's just do some simple steps here. 20 drops per milliliter, roughly, about 20 drops per milliliter. And 1,000 milliliters exactly per liter. So this gives us a liter solution. And then we look over here, that all the zinc in the solid ends up here. And so for every mole of the tetrahydroxyzincate, we had to have 1 mole of the zinc hydroxide dissolved. And so we know the molarity of the tetrahydroxyzincate is going to be 2.6533 moles of tetrahydroxyzincate per liter. And so this gives us how many moles of tetrahydroxyzincate we can get. Then we'll just add in one more. That is, for every mole of zinc hydroxide that dissolves, we form 1 mole of the tetrahydroxide zinc K ion. And then we'll take the molar mass, which, did I erase that? 99? What was the molar mass again? 99.41. 99.41, thanks. Grams per mole. So let's see what we get here. So we'll do 10 drops divided by 20 drops per milliliter, divided by 1,000 times 2.6533 times 99.41. 0.131. And so this gives us this 0.1318 grams. Now, in other words, 131.8. I'm not allowed this many sig figs. About 132 grams or something. Zinc. This we can weigh out, no problem. This we can easily detect. In fact, that turns out to be a significant amount, as it's about 1/10 of a gram per 10 drops. So if we had a gram of it, we just need 100 drops, to dissolve it. And so that's significant. All right, one of the things we do, though, in this type of calculation is we assume that all the zinc just ends up in this one species, the tetrahydroxozincate. But is that always the case? No, like for example, we did the aluminum calculation the other day, but one thing we didn't consider was this. Here it is. Remember visual Mintac? For example, if we look at this aluminum hydroxide here, like if we're looking at aluminum hydroxide solubility, does all the aluminum that dissolves end up in one species? Maybe like the free aluminum? In other words, if we dissolve aluminum hydroxide in water, in our calculations, we only look at one species. All the aluminum hydroxide that dissolves goes to form aluminum 3+ and 3-hydroxide. And so for every mole of aluminum hydroxide that dissolves, I'll form 1 mole of aluminum 3+. But is that the case? No, it's not necessarily the case, because there are other species that occur in the ion pairs, as we saw. And so what happens is we have differences in solubility. And so what we did was, let's take a look. This is going to be another side topic here. Do that over here. We just did a calculation figuring out the solubility of the ice cube here. And so we started off with 0, 0, we ended up with S plus 2S. And so what we assumed is that all the zinc hydroxide that dissolves goes into producing zinc. So all the zinc that was originally in here ends up here. And so we have a 1-to-1 mole ratio of this. But is that always the case? So when we go back over here and we take a look at this, and this is what you guys got to do for yours. So we can run zinc. Actually, you know what? I should run it again. So let's go back to the input menu. What I'm going to do is I'm going to run zinc as a infinite solid. And so let's pick zinc hydroxide. Do you see there's this, sometimes like beryllium hydroxide, or calcium phosphate, or some of these. There are multiple choices here that we can pick. And the same thing for zinc hydroxide. So let me scroll down. So we have zinc hydroxide, alpha, beta, delta, epsilon, gamma. Do you know what those are? Those are like different crystal structures. You know, it depends on the pressure and the temperature conditions at which those form. It's like ice. You know, is there only one form of ice, or are there multiple forms of ice? You guys, jump around this much. Hopefully it didn't log me out. There are multiple forms of ice, which you call ice 1, ice 2, ice 3, ice 4. You heard of those? Show you. What's that? Those in chapter. Carbon dioxide. So if we look at the phase diagram for water, ice 1 is the typical ice that we're used to. But there are higher pressure phases of ice. You subject ice to higher pressures, you can compact the structure more and distort it in such a way. So we have ice 2, ice 3, ice 4, ice 5, etc. So those are just different, we call it different forms of the same element, allotropes. And so the same thing happens here. So we just got to pick one, but which one we pick depends. Probably the alpha form is going to be the most common. And so I'm going to go to specify infinite solid. And let's add a component. Actually, this hung out. So do it one time. Move it out from here. Add that. And then run Mintech. It's hard to see here, so I'm going to go to Excel and blow it up. So what we did was we just assumed that all the zinc ends up in just one species, Zn2+. That's what we do in all these calculations. We just assume that the metal ends up in one species, but in reality it doesn't. If we were just to look at Zn2+, yeah, it looks like it ends up here, but we've got a lot of those species there present. And so in reality, when we're looking at solubility, we have to sum up all these. And so this would equal the sum of all the zinc-containing species. We sum up all those, and then this is the solubility of zinc hydroxide. I got to check the pH because this number is way different than our number that we just calculated. All right, well, the same thing here that I can say about this. We're making the assumption to do this calculation, we're making the assumption all the zinc ends up just in this one species. So here we come up with this mole ratio, 1 mole of zinc hydroxide for every mole of tetrahydroxozincate that forms. But for more advanced stoichiometry problems, you can't do this. So for example, if I were to burn methane and I formed carbon dioxide, carbon monoxide, and soot, then all the carbon from methane ends up into 3 different products. You know, carbon dioxide, carbon monoxide, and soot. And so I can't make a one-to-one assumption. So for every mole of methane that burns, I do not form 1 mole of carbon dioxide. The mole ratio is different. And so the same thing here, if I were to do this at a more advanced level, then what we see is that, oops, which one was it? Well, we see that, no, you know, it actually ends up in multiple species here. And tetrahydroxozincate is just one of these species here. And so, let's set this up. Actually, you know, I just skipped the calculations here. Let me set it up. And so let's set up this problem using Visual Mintac here. In order to set up this problem using Visual Mintac, you know, there are 2 ways I can do it. I can just start from here and going into 6 molar hydroxide, or I can start from here and then precipitate it out. Visual Mintac, even though if you pick infinite solid and you look at the selections, you'll see it's just adding components. And so I'm going to add the components here. The first component I'm going to add is zinc 2+. So let's add the zinc 2+. What molality am I going to use here? I'm going to use 1 molal. 1 molal is too high to sustain at equilibrium. You know, it should precipitate out. So we'll do that. We'll add that to the list. And then I'm going to add some hydroxide to this. If I add hydroxide is not on the list. We have to add H+. So I'll add the H+ here. And then I'm going to make this. Okay, I need 2 hydroxides for the zinc here. And then I'm going to need 6 more. So I'll add a total of 8. So this is going to be -8. I'll add that to the list. And then we'll run Mintac. Then we get this warning. The ionic strength is too high, greater than 1 molar. 6 molar sodium hydroxide should have a pH greater than 14. Should be in the high 14s. And the pHs in the high 14s aren't very accurate because it's going to start to deviate more significantly. And so the activity correction method chosen isn't good or reliable. Well, it's okay. We'll just go with that anyway. And so I'm going to export this to Excel. And then let's take a look at this book here. So I did this 1-to-1 mole ratio here, but that's not correct because all the zinc does not end up in tetrahydroxozincate. Most of it does. You know, if you look at it, compared to the other species, the tetrahydroxozincate is the dominant one here. But if we're doing stoichiometry, then we have to factor in all these species here, not just the tetrahydroxozincate. And so our calculations, are going to be inaccurate because of that. If I really wanted the solubility of the zinc, you know, I'm calling the solubility of the zinc the concentration of the tetrahydroxozincate here. But if I really wanted the solubility of the zinc hydroxide, what I'd have to do is I'd have to sum up. And so this would be equal to sum. I'd have to sum up all the zinc containing species. So line 4 through line 9, I'd add those all up. And then I get this number. And so this is the moles of total zinc dissolved. And so the mole ratio I end up using is the moles of total zinc dissolved related back to the zinc hydroxide, which makes this an advanced stoichiometry calculation. You might have had this in Chem 1A.
maybe, because in one of the advanced problems, there's a stoichiometry problem in which it forms multiple products. But here, for the most part, 99.9% of the problems we do, the zinc is just going to end up in one product. And so it makes the stoichiometry easier versus the reality. The reality is more difficult. And so when we look at the solubility, summing up all the zinc containing species of 0.9872, what was the solubility we just calculated? The solubility we calculated was 2.65. And so there's a difference there. Do you see the difference? Our calculation's quite a bit in error. But the point of all this is this. We're ignoring all this stuff, right? We're ignoring all this stuff, therefore our calculation is going to be off. And so does it make our calculation worthless? No, it does not make our calculation worthless, because this calculation is so easy compared to this this calculation is easy if you have visual mintek, but if you don't have visual mintek, how many ice tables do we have to do simultaneously? We got to do so many simultaneous equilibria here. And so even though we're off, and we aren't off by a huge amount, I mean, just, factor of 2.5 or so, a little more than 2.5, it's still okay, because this is a calculation we can do, and we get some ballpark answer. Okay, so I just needed to talk briefly about that. And so anyway, this is what we did. The calculation wasn't too bad. We came up with this, and this is about the right amount. Now, when I'm starting to do this kind of stuff, I have to realize, I have to keep in mind, this is just a lot of simplifying things I did here, which means that number is going to be off. Okay. Uh-huh.
As you go from 0.12 grams to 120 grams?
Oh, milligrams it's supposed to be. 131.8 milligrams. Which is no problem. All right, so anyway, that simplifies our life here. And then, so this style of problem, we just assume that all the zinc ends up in one of these. Then we can figure out how many moles. And that's our connection. That connection comes afterwards. All right, this is the strategy that we use to dissolve it. We could add some hydroxide to dissolve it, the zinc hydroxide. And the more hydroxide we add, the more it'll get to dissolve. So even though we don't give it a name, we use this for lots of other things. And so let's take a look at an example. We were looking at KSP, so we're looking at salt, dissolving salts, but we could try to dissolve other things. So for example, dissolving metals. In fact, let's look at dissolving gold metal. If we look at dissolving gold metal, is gold soluble in water? No, gold's insoluble in water. And so the only way we can dissolve gold in other metals is by a chemical reaction. It's not by dissolution. When we do a KSP, it's easily reversible. You dissolve the salt, it dissolves, and then you evaporate the water, it reprecipitates. So we can go back and forth. It doesn't change it chemically, it's a physical process. But when we dissolve metals, that's a chemical process. And so we can't just evaporate the water and we'll get gold back again. And so we got to attack it chemically. And so typically when we try to dissolve, let's say, zinc, or we try to dissolve aluminum, or we try to dissolve any metal, we usually use an oxidizer to react it to form ions which are capable of dissolving. And so one of the things we could try is an acid. Acids are oxidizers, mineral acids are, but HCl, not enough. HBr, not enough. Even the strongest acid on that chart, HI, mineral acid, is not enough. We have to go with an oxidizing acid. An oxidizing acid like nitric acid. And so if we try something like nitric acid, which is a decent oxidizer, then the redox reaction is going to look like this. And so it'll be 4H plus a nitrate. I'm just going to write the balanced one here. Gold is going to go through to gold 3. And the other goes to gold 1 or gold 3. Gold 3 is 1 plus NO gas plus 2H2O. It turns out that nitric acid is not enough. You know, the delta G for this is, delta G is too big. You know, there's an easy way of determining delta G's for this. One of the easy ways of determining delta G's is by using cell potentials. And so I'm going to go to Appendix D, and we're going to look at the redox chart for the table of the standard reduction potentials. And looking at the redox chart here, you know, fluorine's going to have what we call the highest reduction potential, it's the strongest oxidizer. And then we go down the list here. Here's permanganate, hydrogen peroxide. Here's one we saw yesterday. What was this one? Do you recall where we saw PbO2 plus sulfate plus 4H pluses? The PbO2, this is for car batteries. This was the oxidizer in car batteries. Okay, here's gold. And so do you see gold goes to gold 3 if we reverse that? And so gold 3, what would you say? Gold 3 has a relatively high reduction potential, oxidation potential, or moderate or relatively low. So if we're looking at gold 3 ion, what would you say? How would you describe it? In terms of reduction and oxidation potential. Is it reduction? Okay. And then would it be high or low?
Medium.
Medium high? Well, it depends. This table's long. Let's show. Oh, shit. All right, so that was page 1. This is page 2 of that chart. And then it goes on to page 3. Page 3. And so what would you say about gold 3? Gold 3 would be
High reduction.
high reduction potential. Which means it's a good, if it has a high reduction potential, it's a good oxidizer. And so gold 3 is a good oxidizer. Well, what does that say about gold? Gold is its conjugate. Gold metal is its conjugate. If gold 3 is as an oxidizer, then gold metal is its conjugate reducer. Now, what can we say about gold metal? So we just said about gold 3, but I don't have gold 3. Gold 3 is my product. I'm looking at gold metal. And so what can you tell me about gold metal? It has a what? Strong oxidizing potential? No. No. Weak. Yeah. Right. This is the conjugate relationship. So if gold 3 has a high reduction potential, then gold metal will have a low oxidation potential. A low oxidation potential means it's hard to oxidize. Right? And what it means is it's not a very good reducer. And what is that oxidation potential? Well, the oxidation potential for gold is minus 1.52 volts. And so an easy way to figure out the cell potential here is just, we look at gold going to gold 3. This would be the couple. And gold going to gold 3 is minus 1.52 volts. And then the other potential we're looking at is nitric acid. Okay, where's nitric acid here? So we'll go down the list and we'll look for nitric acid. It's way down here. And I've always called nitric acid a good oxidizer. And so nitric, even though it's kind of mid-range here, it's a good oxidizer. And so here we have nitrate and H+. And so we're going from nitrate, this is under standard conditions here, H+ to NO gas. And so this would be the couple. And so nitrate's a pretty good oxidizer because it has a fairly high, what do you call that? Reduction potential. This reduction potential is 0.956 volts, which is okay. So this is 0.956 volts. But if we want the cell potential, we have to add the, what do we call this one? We have to add the oxidation potential plus the reduction potential to get the cell potential. And so the cell potential for this is going to be equal to minus 0.564 volts. A minus 0.564 volts, is that good? No, what this means is this is non-spontaneous. We need a positive voltage, right, to get it. Now, how non-spontaneous is that? Well, we could just use delta G. Since this is under standard conditions, delta G naught is going to equal minus Z F E. And so this is under standard conditions. Z, how many moles of electrons are transferred in the balanced redox reaction? 3. And so this is going to be minus 3 moles, and then F is 96,485 coulombs per mole. You don't have to memorize that. I'll just give that. The moles cancel. E naught of the cell is going to be minus 0.564 volts. A coulomb times a volt is a joule. And so we can figure out how many joules this is. And so doing that, it's going to give us, let's see, 3 times 96,485 times 0.564 gives us let me make sure I did that. Well, I'll do it in kilojoules. It gives us negative 163, or actually negative times positive 163.2 kilojoules, which means it's highly, highly non-spontaneous. And so, do we have any luck? Would we have any luck dissolving the gold? Not under standard conditions. We won't have any luck. The gold will not dissolve in nitric acid. Nitric acid will dissolve silver, no problem. It will dissolve copper, no problem, but not gold. And so we need a little help here to do this. And the little help here is like gas formation. Gas formation is a help because if we can blow out the gas, the NO gas, then if we can get rid of the NO gas, then that will help shift this to the right. And so getting rid of the NO gas helps, but not a huge amount, not enough to get this to dissolve, unfortunately. So what's one other way? Well, we could think about gold, you know. We can think of something to remove the gold. 3. And so we could try to precipitate it, but if we precipitate it, then we get a mixture of 2 solids. A mixture of 2 solids is always a hassle. And so we don't want to precipitate it. In fact, and so we probably wouldn't look at the KSP table, even though, unfortunately, gold's not there. We'd probably try to complex it because a lot of these complex ions are soluble in water. And so what we do is we look, does gold like to form any complexes? Well, silver likes to form lots of complexes. Take a look. You know, anywhere from the cyano to the thiosulfato complex. Silver has a bunch. Aluminum. Do you see any gold there? No. And so does that mean gold does not like to form complexes? No, it just means that this table is not complete. This table is not complete because gold does form complexes, and in fact they showed one of them if you looked at the redox chart. So let's go back and revisit the redox chart here. What did we say about gold metal? Gold metal has a low, what? Low oxidation potential, means it's hard to oxidize, minus 1.52 volts. Okay? But as we go down the list here, we come across something. Here's gold ion, but we don't have gold ion. As we go down the list, we see gold metal appear again. Here, gold metal in the presence of chloride. Gold metal in the presence of chloride is minus 1 volt. And so minus 1.52 volts versus minus 1 volt. Minus 1 volt is a higher oxidation potential by a half a volt. And so if we have gold metal in the presence of chloride, that has a higher oxidation potential than gold metal alone. What this is, it's the combined method. And so they should have shown this here, but what we have is gold. If we have solid gold going to gold 3 plus 3 electrons, this has a low oxidation potential. One way we can increase that oxidation potential is try to do a Le Chatelier's shift. One way to do Le Chatelier's shift is try to complex the gold. So if we take the gold 3 ion and complex it with 4 chlorides, then we can form this ion, the tetrachloroborate ion, which is going to have a minus charge here. And so this is the combined method. So if I combine these two, I get gold solid plus 4 chlorides goes to tetrachloroborate. Okay, this is going to have a much higher oxidation potential because we're removing, the gold 3 out of there. So this is a combined method, it is working in a different way than what we saw with the KSPs. It's the same thing here, okay, here we're going to generate the gold 3. And when we generate the gold 3, what we'll do is we'll take out the gold 3 by complexing it with chlorides. And then we'll end up with tetrachloroborate ion here. And then we combine these, so we're going to combine a KF and then the K redox here. And so this would be a K redox F. And so the net reaction here is this. The net reaction is nitric acid and chloride will do it. And so usually here we use aqua regia. Aqua regia is a mixture of nitric acid and hydrochloric acid. The purpose of the nitric acid is to oxidize the gold 3. The purpose of the hydrochloric acid is to complex it. And so this is gold dissolves in aqua regia, but it won't dissolve in nitric acid alone, and it certainly won't dissolve in hydrochloric acid alone, but it will dissolve in both nitric and hydrochloric acid combined. And so it's the same strategy. And so this is the type of stuff we look for when we're doing chemical reactions. We look for things like this, qualitative analysis and dissolving stuff, as far as that goes. All right, so I'll stop here. Actually, I'm not done with chapter 18. I just have one little thing to talk about. I'll talk about it tomorrow. Actually two. So we'll talk about it. So we didn't get to sulfides.